Hello, everyone, and welcome back to my channel. I'm sorry I haven't been able to record a video in 2 or 3 months. It's because school was a bit busy, test projects, finals, all that. And my summer's a bit busy too, but I think I can get the entire channel up and running in September, after everything calms down a bit. But for now, I wanted to surprise you with a new playlist. It's called The Specials. And in the specials, I don't teach a hardcore subject like I do in the other channels. What I do instead is I teach you a little bit of learning, and then introduce you to something fun or odd in a subject. In this case, it's math. I'm going to talk to you about infinite arithmetic series. This is the first special, so it's extra special actually. Let me know how you think about this. Do you want me to continue this channel, or if you think it's boring and just want me to teach other subjects? Let me know in the comments below. Back to this though, infinite arithmetic series. It's about math. Now, for those of you who haven't taken Algebra 2 or pre-calculus yet, I'll do a bit of learning, teaching actually for you before I actually get into what this is about. So let's break this title into 3 parts: infinite, arithmetic, and series. We'll go from right to left. What's a series? Well, before I tell you about series, I'm gonna have to tell you about sequences. A sequence is basically a set of numbers that follow a particular pattern. So 2, 5, 8, 11, 14. That's a sequence. And do you know what the pattern is? Well, you just add 3 to each term. 2 plus 3 is 5, 5 plus 3 is 8, and so on. This 3 is called the common difference because the difference between any 2 consecutive terms is 3. 5 minus 2 is 3, 8 minus 5 is 3, and voila, 11 minus 8 is 3, 14 minus 11 is 3. Something else you might want to know about sequences is the initial term, A1. And A1 is basically the first term. In this case, it's 2. Given these two, A1 and D, you'll be able to find any sequence. So a little bit of practice. Let's say A1 is 7 and D is, let's make this a bit hard, negative 2.5. Gotta love decimals, huh? So what's the first term of this? Well, trick question. The first term, we're given it, 7. That was easy. Now, a second term is a bit more hard. How did we get the second term of this? Well, 2 plus 3 is 5. Third term, 5 plus 3 is 8, and so on. So the second term of this would be 7 minus 2.5. You might be thinking, why minus? Well, that's because I made this negative just to have a bit more fun. The negative means we have to subtract. So 7 minus 2.5 is 4.5. 4.5 minus 2.5 is 2. 2 minus 2.5, negative 0.5. Negative 0.5 minus 2.5, negative 3, and so on. This is a sequence that we made. Our first sequence, yay! Now that we're done with sequences, we'll talk about series, actually part of the title. So a series is basically the sum of a sequence. So 2 plus 5 plus 8 plus 11 plus 14 is the sum of the sequence we talked about first. Now, what's the sum? Well, that's easy. We just add all the terms. 2 plus 5 is 7, 7 plus 8 is 15, 15 plus 11 is 26, and 26 plus 14 is our final answer, which is 40. Yes. Now, that's all. Well, we got a third of the title. That's already an achievement. What about arithmetic, though? Arithmetic is a type of sequence and series. You've probably heard of arithmetic sequences and arithmetic series if you went to Algebra 1 or Algebra 2 or pre-calculus even. But I'm here to tell you that I already told you about arithmetic sequences and series. An arithmetic sequence is basically a sequence that has a common difference between every 2 consecutive terms. Does that seem any familiar? Well, that's basically this thing right here. That's the first thing I told you about. It has a common difference. So unknowingly, I just told you the definition of an arithmetic sequence without telling you that it was an arithmetic sequence. Okay, I'm going to stop now before I confuse myself. Now, arithmetic sequence, in fact, both of these are arithmetic sequences because the definition is that it has a common difference, B. If it doesn't, then it's not an arithmetic sequence. There are other types like geometric and harmonic. Those both are cool. But today we're going to be talking about arithmetic sequences in series. So if you want, you can search them up. Arithmetic series is this thing right here. You add up an arithmetic sequence. So all's well. 2 out of 3, not bad, right? Just a quick note, actually, there is a formula for the sum of an arithmetic series, but I want to mention that, like I said, it's only a little bit of learning for what's relevant, and you're not really going to need the formula for the series. Back to the third part, infinite. This is where things get a little bit tricky. Well, infinite just means to go to infinity, right? Like infinity and beyond, like in Toy Story. In this case, if you want to add on to infinity, you follow the same pattern. 14 plus 3, 17, 20, 23, and so on. 26, 29, 32, 35, 38, you know, all this good stuff, all the way up to infinity. Now, if you were to ask your middle or high school teacher, does this exist? Like, is this a valid sum? Let's just ignore the plus 40 right now because we're talking about the infinite one. And your teacher's probably going to tell you, no, it doesn't exist because you can't go all the way up to infinity. It's like adding on something forever. You're just going to get infinity, which is not a real number. So they're probably going to tell you it does not exist. This D and E means does not exist. You'll probably find that on calculus. Limits does not exist. Now, if you haven't done calculus yet, sorry for the terminology. Calculus is pretty fun though. Anyway, D and E does not exist. They're probably going to tell you that. But what if I were to tell you that that's not the case at all? It does exist. The sum does exist. You probably are a bit skeptical. I mean, after all, I'm not your teacher. But let me prove you something. I'm going to prove you that there is a sum of an infinite arithmetic series. Let's take the most basic one. 1 plus 2 plus 3 plus 4 plus 5 plus 6, and so on all the way to infinity. This is the most basic one. Common difference is 1. First term is 1, you know. And let's say I say this is equal to the variable s. S is the sum of all of this all the way to infinity. Now, you're probably thinking it doesn't exist, but since I told you that it does exist, you might be having second thoughts. And what if I were to tell you that, yes, it does exist. It's not infinity. You might be thinking it is infinity, but it's not. It is a finite number, meaning it's not infinity. Now, what if I told you that number was negative? What if I told you that that number was a fraction? What if I told you that the sum was negative 1/12? You'll probably never believe me again. But if I prove you enough, maybe you will. So without further ado, let's get into the quote unquote fun part of the video. I'm going to prove you this very odd phenomenon. Before I prove that to you though, I'm going to have to make a few more variables. I'm going to say another series, S1, would be the series 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on, plus dot dot dot, all the way to infinity. Again, an infinite series, but this time it's not arithmetic. It's a weird series. It's called an oscillating series because it oscillates from one point to another, from positive to negative to positive to negative, positive to negative, like that. Like a pendulum, kind of, if you've ever seen it like go back and forth. But that's physics, that's for another day. Anyway, what would the sum of this series be? Well, you'll be like, that's easy, it's just it's just 0, right? Because you take 1, you subtract 1, take 1, subtract 1, and so on, right? Whatever you take, you subtract it. Now, I might have spoiled the surprise because I actually said 1 instead, but the sum is also 1. The sum is 0, yes, I agree with you, but it's also 1. Because let's say you stop at this point, well, the sum is just 0. 1 minus 1 is 0. But if you stop at this point, it'll be 1 minus 1 plus 1, which is 1. You never know what infinity is. If it's an even number, you stop at this point. If it's an odd number, you stop at this point. So it's either 0 or 1. And both have an equal chance of being right. You don't know if it's even or if it's odd. If you don't know if you stop at a 0 or you stop at a 1. So therefore, the sum of this is actually 0 plus 1 divided by 2, the average of the two possibilities. That might not make sense to you, but its probability is just 1/2. Now, if you're still not satisfied, you might think this proof has a few holes in it. Let me explain it to you. Let's say I take S1 and I subtract 1 from it. Just so you know, if you are satisfied with the proof I gave above, you can skip forward until I prove the next part of it. But if you really want to test my mathematical abilities, feel free to watch this proof. So this is another proof to show you again that the sum is 1/2. S1 minus 1. So if you remove 1 from it, let's just take off the first term because that's 1. That'll be -1 plus 1. Ooh, that's a horrible addition sign. Plus 1 minus 1 plus 1, and so on. Now, this looks a bit familiar, doesn't it? If you were to negate everything, so it'll be negative, basically take a negative out. That's what it means by negating everything. -1 minus 1 plus 1. So every sign basically becomes the opposite. -1 becomes +1, +1 becomes -1, negative, positive, positive becomes negative, +1, minus ... That looks a bit familiar, doesn't it? That's basically this sequence. Well, without this erasing. That's basically this sequence, right? And it is. So this is basically just S1. We just proved that S1 minus 1 is equal to negative S1. Because remember, we took the negative out, so there's still the negative there. Now, we just use a bit of algebra. Take the S1 to this side, so it'll become 2S1 minus 1 is equal to 0. Take the 1 to that side, 2S1 is equal to 1, and divide by 2. Final step, S1 is equal to 1/2. And voila, I proved it to you. Another way, of course. The first one was perfectly fine, except for those of you who didn't like it. S1 is equal to 1/2. This sum, which has no fractions whatsoever, has a sum of a fraction. That makes no sense to most of you, but that's the way math works. That's why I made this a special, because it's a fun and odd phenomenon in math, doesn't it? Well, it's not over there, because we still have to prove my first original statement that the sum of the infinite arithmetic series is possible. Now that we did this, how does that have anything to do with this series? Now, I'm going to create another variable, S2, and that is a somewhat related series. It's going to be the series 1 minus 2 plus 3 minus 4 plus 5 minus 6, ... That's still not arithmetic. It's a slightly different oscillating series, because again, it's going from positive to negative. But now, instead of going like that, that is sort of like this series. This series is going like that. Oh God, I just tore over the entire board. Anyway, hope you get what I mean. It's like really weird. You can't even guess what the sum of this would be. I mean, you can guess that the first one's infinity and the second one is either 0 or 1. This one, it goes to infinity if you stop at this point, and negative infinity if you stop at that point. Okay, how are we going to prove this? Well, let's say this is S1 and this is S2. Let's subtract the series from each other. S1 minus S2. Note that we still haven't found a value for S2, but we're going to use this to prove a value for S2. So what's this? 1 minus 1. I'm just going to write the first 4 terms of each series and then ... just to make my life a bit easier. That minus 1 minus 2 plus 3 minus 4 ... So what would that be then? Well, let's take it term by term. 1 minus 1 is 0. -1 minus -2. So that's a bit weird stuff, right? -1. So this minus basically contracts this minus, so it becomes +2. -1 plus 2, well, that's +1. +1 minus +3. So that contracts the positive and makes it negative. So it'll become 1 minus 3. So it'll be -2. -1 minus -4. Again, this becomes +4. So it'll become +3. And if you do the next few terms, which I'll just show you what they are, it'll be -4 plus 5 minus 6, and so on. Now you might get where I'm going with this. This looks awfully familiar, doesn't it? It's basically the same thing as S2, except it has a 0 in the front, and the 0 makes no difference here. Get out of here, 0. This is basically equal to S2. Now, I'm going to go up here where I have a bit more room. If we simplify the equation, we're going to say S1 minus S2 is equal to S2. Aha. So now there's only one variable because we already know that S1 is equal to 1/2, right? S2 is the only variable. So like we did last time, take the S2 there. 2S2 is equal to 1/2 because 1/2 is S1. And divide by 2. S2 is equal to 1/4. That's right. This is equal to 1/4. Neither infinity nor negative infinity, but it's not negative 1/4. It's just 1/4. Think about that. How do you get this stuff? It's just amazing, isn't it? So that's the proof for that one. Now we're finally ready to prove what we started with. We'll prove that S is equal to negative 1/12. Once I finish erasing all this. How do we get from here to there? See if you can do it. I'll give you a few seconds. Okay, we're gonna basically do the same thing that we did for the second one. We're gonna do S2 minus S. So it'll be, this time I'm gonna save myself some trouble and not write both series down. I'm just gonna do it manually. 1 minus 1 is 0. Negative 2 minus negative 2, minus positive 2 is negative 2 minus 2, negative 4. 3 minus negative 3 is 0. Negative 4 minus negative 4 is negative 8. Sorry, why do I keep on doing this? Negative 4 minus positive 4 is negative 4 minus 4 is negative 8. 5 minus 5 is 10. Sorry, 0. Negative 6 minus 6 is negative 12. And so on. This may not look like anything to you, but a few more terms. So far we have 0, negative 4, 0, negative 8, 0, negative 12, 0, and then negative 16, 0, negative 20, 0, negative 24. Now there might be a pattern. Well, first we can get rid of the zeros like we did last time. And then if we write this, we will get negative 4 minus 8 minus 12 minus 16 minus 20 minus 24. Now what's that? Oh, and so on, of course. And that's basically this series, but you multiply by 4 and negate it. Because when you multiply by 4, you get 4 plus 8 plus 12 plus 16 plus 20 plus 24. And when you negate it, you get negative 4, negative 8, negative 12, negative 16, negative 20, negative 24, so on. So this is basically equal to negative 4s. Again, going up here and cleaning up everything. S2 minus S is equal to negative 4s. Take the s to that side. S2 is equal to negative 3s. And I'm going to replace S2 with the value we already know for it, which is 1/4. So divide by negative 3, you get S is equal to negative 1/12. Voila. Finally, what you've probably waited the past, I don't know, however long I recorded this video for. S is equal to negative 1/12. The sum of this infinite arithmetic series is negative 1/12. Now, you might think I'm probably going to end the video there, but no. I'm going to prove to you that every single arithmetic series exists. Infinite arithmetic series exists. Not just the basic 1, 1 plus 2 plus 3 plus 4 plus 5 plus 6. Of course, I'm going to use this series to prove it. But I'll get rid of everything else until then. If you want, take a little break while I try to erase everything else. Oh God, you hate it. Gotta hate erasers. Okay. Let's say we have a random arithmetic series. And now this is why I told you about initial terms and common differences. Let's say the initial term was A and the common difference was D, meaning that the first term in the sequence would be A. Second term in the sequence would be A plus D. Third term in the sequence would be A plus 2D. And so on. Now, like I did before, I'm going to give you a few seconds to try and figure out why this correlates with that. How can you even prove it? Go on, take your time. Okay. If you didn't yet prove it, well, what I'm going to show you now is probably worth it. If you did prove it, congratulations. Now, if I write a few more terms, which I'm not going to because too much work, you'll probably see a pattern. A plus 2D, A plus 3D, A plus 4D, A plus 5D, A plus 6D, right? Meaning 1D, 2D, 3D, 4D, and so on. This many Ds, right? So the easy part is the A's. There's always going to be infinity A's no matter what. You'll have one A here, two A's here, sorry, one A here, total of two, one A here, and one for every term. And like I said, there's infinity of them. So it's going to go on to infinity. Now, if you notice this, notice anything familiar about this, wait till I'm done. And that's when the actual brilliance is going to hit. So that's how many A's there are. A as in the variable, meaning the first term. Now, what about the D's? We have 1D, 2D, 3D, 4D, 5D, 6D. And no, I'm not talking about dimensions. It'll be cool if we had that many dimensions. But anyway, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6, and so on. And that's how many D's we have in this entire sum. For those of you who are observant, you would have noticed this. This, I did not prove what it is equal to, but I'm gonna quickly prove. If you notice, it's similar to the 1 minus 1 plus 1, which is what I wanted you to notice earlier, but I told you to keep quiet until I showed you everything. This one, right? But it's different because it's all positive. It seems a bit like the other two we did, S2 and S. One was the 1 plus 2 plus 3 plus 4 plus 5 plus 6. The other was 1 minus 2 plus 3 minus 4 plus 5 minus 6. In this case, it's similar. Let's say that this sum we'll say is S3, and we already said this is S1. Again, we can subtract both of them. Let's work. S1 minus S3, right? So 1 minus 1 is 0. Negative 1 minus 1 is negative 2. 1 minus 1 is 0. And this time I'm not messing up on the zeros. I'm not saying 1 minus negative 1. Always achieve something new. Negative 1 minus 1 is negative 2. 0, negative 2. I think you can see a pattern here. It's basically when you do 2 times, well, first when you get rid of the zeros, it's negative 2, minus 2, minus 2, minus 2, minus 2, and so on. It's when you negate 2 times S3. Because 2 times S3 is 2 plus 2 plus 2 plus 2 plus 2. Negate that, you get negative 2 minus 2 minus 2 minus 2 minus 2. So therefore, we have S1 minus S3 is equal to 2 or negative 2 S3. I'll erase this little part right here. So I have room to show you. When you add negative S3, sorry, when you add S3 to both sides, you get S1 is equal to negative S3, and therefore S3 is equal to negative 1/2. So yes, there are no negatives in this, yet it's still equal to negative 1/2. I know it's a bit hard to believe, but you got to trust me on this. Now that we know that S3 is equal to negative 1/2, time to erase all of this. And time to get back to our regular one, our regular proof. This was just an intermediate proof, something I had to do in between. So we know this, we just proved is negative 1/2. And we know this is already negative 1/12, meaning that the sum of this series, let's just say S infinity, is equal to, I don't have room, okay. S infinity is equal to negative 1/2 A minus 1/12 D. And you can use basically any formula or any sequence series you want and find the infinite arithmetic series of it. Well, provided that it's an arithmetic sequence. Like the first one we did, where it's A1 is 2 and the difference was 3. That's the 2, 5, 8, 11, 14, 17, 20, 23, so on, sequence, series. Now you add everything up, or you can just use this formula. It'll be negative 1/2 times A. So you plug in 2 there, you get negative 1. Negative 1/12 times D, you get negative 1/4. So the sum is negative 5/4. And yes, I know it looks crazy like everything else I showed you in this video. And it might not even be true. There might be a hole in this proof. But as far as physicists and mathematicians are considered, this is true. This is even an application in string theory. Infinite arithmetic series, who knew? String theory is astronomy, astrophysics, cosmology too, a bit. Anyway, now with this video, I'm not trying to make you write this answer on a test in your class. Let's say they told you find the infinite arithmetic series of this. They're probably expecting you to write it doesn't exist because that's what they teach you in high school. And I'm saying on that test, write it doesn't exist, even though you know that this is true. This is a disclaimer, basically. I don't want you to write this on a high school level because this is a bit more advanced. It's not what they teach you in high school. So that's it for this video, basically. If you like this kind of content, this fun new approach to learning, just let me know in the comments. Like I said, I'll be happy to do a few more videos like this. But of course, I'll get back to our regular learning, our actual subjects, back maybe in September. But until then, I'll see you then. Have fun.